Hello and welcome to lecture 10. In our last session, we were discussing about axial, radial and tangential momentum, and we have realized this is what is in relation with your mechanical part, but still the change of velocity components named say axial velocity, tangential velocity and radial velocity, they are having their own importance. If you look at next, we have discussed about the different types of stage arrangement for axial flow compressor and fans. What all configuration we have discussed is with only rotor configuration, say stage with inlet guide vanes. So we will be having say inlet guide vanes that will be followed with rotor. We have stage with outlet guide vanes, means rotor will be followed by the stator. We have inlet guide vane as well as outlet guide vane, and we have discussed important aspects for the contra rotating or counter rotating fan or compressor configuration. So, in our configuration for our understanding, if you look at here, say when we are using only rotor configuration, we realize we will be having whirl component, that's what will be coming out from the exit. And we realize based on our requirement, we need to design our fan. So when we are not expecting much pressure rise and our whole purpose it is for handling the mass flow rate, this kind of configuration, that's what is preferred. We have inlet guide vanes, that what will be followed by your rotor. Under that configuration, we try to avoid the whirl component, that's what is coming out from my rotor. And if that's what is your case, you need to have your rotor inlet condition at certain angle. So my inlet guide vane, that's what will be providing my flow to the rotor at certain angle, and my exit we are considering to be axial. Here we are try to avoiding the whirl component. Okay. Same way here, if we consider we are having rotor that will be followed with the stator. So here also we are trying to remove the whirl component coming out from the rotor, and we are trying to give the axial exit. It is based on the requirement. In line to that, we can have configuration in which we are having say inlet guide vane that will be followed by rotor, and that will be followed with my stator configuration or say outlet guide vane. Then we have discussed very important aspect, that's what is say our contra rotating fan or counter rotating fan or compressor, in which we have utilized the whirl component that is coming out from my rotor 1 that will go inside the rotor 2, that's what will be sucked by rotor 2, which will be increasing our relative velocity at the entry of my rotor 2. And we will be having comparatively high pressure rise compared to all this configuration. And we have discussed this configuration, that's what is having now more attractions for future engine developments. Now, if you want to have the idea, let's take one of the tutorial which will give you idea what all we are discussing in sense of stage configuration, how do we use that for our purpose. So take one numerical, say we have an axial flow fan that need to be designed for axial velocity of 40 meter per second, rotor speed is 1500 rpm, my flow turning angle is 15 degree for the rotor, mean line diameter or mean line radius for the stage is 0.5 meter. Consider say flow is entering axially. Evaluate the static pressure rise and specific power for each of the following cases, in which we are having without guide vane configuration and we have inlet guide vane configuration which has absolute entry angle at absolute exit angle of minus 25 degree, and my discharge is axial 1. Now for this configuration, what all data we know is we are having our axial velocity, it is 40 meter per second. We have our peripheral speed, we can count by using my rotational speed of 1500 rpm. For rotor, my delta beta, that is my flow deflection angle, it is given 15 degree. Now let us see, suppose if I am taking my case 1, which is say without guide vanes. So in order to understand that, we can have this as a line diagram. We can have our station 1 and station 2. For that station 1 and 2, we can make our velocity triangle. It says my entry to the rotor is axial. So we can say this is what is my axial entry. So this represents my inlet velocity triangle, and this is what is representing my outlet velocity triangle from the rotor. Now what we want to calculate? We are looking for what is my static pressure rise in the rotor. That's what is given by half V1 square minus V2 square. Second, we are looking for specific power. That's what is U into CW2. It means with given data, we need to calculate our peripheral speed. We need to calculate what will be my relative velocity at the entry, what will be my relative velocity at the exit. We are looking for what will be my swirl component or my whirl component coming out from the rotor. With this data, let's start with. So very first point we can say we are looking for calculation of peripheral speed. So my mean radius, that's what is given to me, it is say 0.5 meter. So from that we can calculate what is our peripheral speed. So this peripheral speed I can write down 2 pi Rn by 60. So this rotational speed is given, it is 1500, and my radius, that's what is given 0.5. So we can calculate what is my peripheral speed. So it says this is coming 78.54 meter per second. Now we have our next parameter that need to be calculated. That's what is say we are looking for my V1, that's what is my relative velocity at the entry of my rotor. So based on my velocity triangle, I can write down my 10 beta 1, that is U by Ca. Since my entry is axial, so we can write down U by Ca. We know what is my peripheral speed now. We know what is my axial speed or axial velocity. So if I am putting that number, it says my blade angle at the entry, it is coming 63 degree. Now what we know, we have our delta beta, that's what is known to us. So let me put delta beta, that is beta 1 minus beta 2. It is given that angle or the difference is 15 degree. So I can calculate what will be my beta 2. Now once my beta 2, that's what is known, my beta 1, it is known to me, I can calculate what will be my speed. So that's what is say my relative velocity at the entry. It is U by sine beta 1, you can say by using velocity triangle. So that's what is giving me my relative velocity to be 88.14 meter per second. Now we are looking for our exit condition because we want to calculate what will be my relative velocity at the exit and what will be my whirl component. So in order to do that calculation, from our velocity triangle and from geometry, we can write down U by Ca, that is 10 alpha 2 plus 10 beta 2. Since my beta 2 is known to me, I can calculate what is my alpha 2. So if I am putting these numbers, it says my alpha 2 is coming 40.44 degree. Once my alpha 2 is known to me, I can calculate what is my tangential speed or tangential velocity. So CW2, that is given by Ca into 10 alpha 2. So if I am putting those numbers, my axial velocity is known to me, it is 40 meter per second, and alpha 2 we have calculated 40.44 degree. This is giving me my whirl component, or say whirl velocity at the exit of rotor as 34.1 meter per second. Now what we are looking for is at the exit. We are looking for our relative velocity at the exit. So based on my velocity triangle, I can write down my V2, that's what is given by u minus Cw2 divided by sine beta 2. If I am putting these numbers, it says my relative velocity, that is coming 59.8 meter per second. So now in order to calculate what is my static pressure rise in the rotor, I will say my delta P, that's what is given by half rho V square. Okay, it is V1 square minus V2 square. So if I am putting this number, I am looking for my density. Let me assume, since density is not given, I can safely assume density as 1.225 kg per meter cube. So this is what will be giving me my delta P across the rotor, means static pressure rise across the rotor. So this it's coming 2568 Pascal or 2.56 kilopascal. We are looking for specific power. This specific power, it is given by U into Cw2. So my peripheral speed is known to me, my Cw2, that's what is known to me. If I'll be putting this number, it says my specific power, that is coming 3176.16 joule per kg. Be careful about the units. Now we have our second case, in which we have our inlet guide vane, in which my flow is entering inside the rotor at some angle alpha 2, that's what is given, say it is minus 25 degree. And here if we are looking for, we want to calculate our static pressure rise in rotor, we are looking for our static pressure rise in the stator, or say inlet guide vane, that's what is given by half rho V2 square minus V3 square for my rotor, and for stator it is 1/2 rho C1 square minus C2 square. And my specific power, if I am looking for, it is U into Cw2. So here in this case we are looking for calculation of my relative velocity components V2, V3. We are interested in what is my absolute velocity C1, C2, and we are also interested in what is my Cw2. Now let's start from the exit velocity triangle. We can straightway write down my beta 3, that's what is a function of U and Ca. So since my exit it is axial 1, we can say tan beta 3, it is U by Ca. If I am putting these numbers, it says my beta 3, that's what is coming 63 degree. Now what is known to us, we know my delta beta, it is given say 15 degree. Since we have calculated our beta 3, so we can calculate what is our beta 2 angle, and that beta 2 angle is coming 78 degree. Now once this is what is known to me, based on my velocity triangle, we will try to calculate what will be my Cw2. So this Cw2 we can write down, it's Ca tan alpha 2. This alpha 2 value, that's what is given to us, it is minus 25 degree. So we can calculate our work component. It is minus 18.65. Remember the thing, where we are putting our inlet guide vanes, that's what will be deciding the magnitude of my work component. We can calculate our relative velocity based on the velocity triangle at the entry of my rotor. It says relative velocity V2, it is U minus CW2 by sin beta 2. I know what is my U, I know what is CW2 and what is my beta 2. So, based on that, we can do our calculation for relative velocity. This relative velocity, it is coming 99.36 meter per second. If you compare with the earlier number, when we are having only rotor, there this relative velocity coming to be lower. Now, since we have provided with our inlet guide vane, this relative velocity is going to increase. Now, we are looking for what will be our exit relative velocity from this rotor. That's what is given by U by sin beta 3. So, if I am putting that numbers, that's what is known to us, we will be getting our relative velocity to be 88.14 meter per second. So, once this is what is known to us in sense of relative velocity at the entry of my rotor and at the exit of my rotor, we can calculate what will be the static pressure rise in the rotor. So, that is given by 1/2 rho V2 square minus V3 square. Since my V2, that's what is known to me, we have already calculated, and my V3 is also known to me, we can calculate what is my delta P0. That's what is coming 1289 Pascal. Now, what we know what is our absolute velocity at the rotor entry. That's what is given by Ca by cos alpha 2. That's what will be giving me my absolute velocity as 44.14 meter per second. We are interested in calculating what will be the static pressure rise in our stator. If I am putting this number, it says 1/2 rho C1 square minus C2 square. So, if we are putting our C1 and C2, it says my static pressure rise, that's what is coming, minus 213 Pascal. Now, since we have our total pressure rise in rotor, we have pressure rise in stator, we can calculate what will be my net pressure rise. So, this is what is coming 1076 Pascal. We are interested what is our specific power, that's what is U into CW3 minus this. So, if we are putting these numbers, it says my specific power, it is coming 1464.77 joule per kg. So, basically for solving this kind of numericals, you need to make first the sketch, rough diagram, what instructions, that's what is given. Then after you have your understanding of velocity triangle, look at what angles are given. Based on that, you construct your velocity triangle. Once these velocity triangles are known to you, you just put what all velocities are known to you. If we have those velocities known, based on our trigonometry, we can calculate the velocity component or say angle components. Once we are calculating our velocity components, if we are calculating relative velocity components, that's what will be helpful for calculating my static pressure rise in rotor. If we are calculating absolute velocity component, that's what will be helpful to us for calculating static pressure rise in my stator. And work component, that's what is helpful to us for calculation of our specific power. So, I am sure this is what will be giving you idea in sense of how to do this calculation for different configurations. We have 5 different configurations which are possible. You can do practice, based on your understanding and build your confidence. Thank you. Thank you very much for this session. See you in the next lecture.